All right, so let's take a second here and make sure that we've labeled everything. This is our simplify. Here we have our tree statistics. This was our decompose, right, which turns our paths into lists of index values. This is our flip matrix, explode tree, test for equality. All right, so now we have a list of trues and falses and a list of the original paths. So let's use some of the list manipulation tricks we went over in some of the previous courses we've offered. Under sequence, if we use the cull pattern here, we can remove all of the paths that do not meet this test, right? Or that, in this case, the test is what we want to remove. So we're going to use the does not equal sign. So you can see here that 0, 0 is removed, 1, 1 is removed, and 2, 2 is removed. Right? And this is going to work no matter what the condition of intersections is and no matter how many curves we have. Right? I could draw another curve and add all of those into the original input, and this is still going to remove those duplicates. All right, now all we've done really, though, is we've removed the paths from a list of paths. In order to remove them from the data structure, what we're going to do is we're going to use that object that we were talking about a second ago, which is the tree branch. So this retrieves a specific branch from the data tree, and these are all the branches that we want to keep. So we're going to put those into the P input, and from simplify, all the way back there, we're going to take the original data tree and only keep the ones that are meeting the condition. Right? So now if I turn the previews off of everything, you'll see that I don't have the ones on the endpoints, which were just the self-intersection. I have these, and if I were to look at the data structure, I'd notice that in these locations I'm going to have 2 points. One for this curve and one for this curve. All right, so this was the tree branch object. And we're cruising along pretty well, right? Now we want to just do something with the intersection points that we have. Let's find some geometry to create there, right? So if we imagine that we're going to draw a rectangle that looks something like this at every one of these locations, right? That's going in the direction of the curve and its midpoint is passing through the intersection, right? Then we just need to go back to the curve to find some more information about that curve so that we can draw the corresponding rectangle. All right, so if these are our points, and they're organized in a data tree with 2 levels, where now A is the original curve and B is the intersecting curve, right? In order to get all of these points to be related back to their original curves, we need to remove one level of the data tree so that all of the things that have the first index in the data path as 0 will correspond to the curve that's labeled 0 in the original grafted list. All right, so the way we're going to do that is that we're going to use the shift paths object, and this allows us to shift the collection of indices that compose a path. So what was a 3-level data structure will go back down to a 2-level data structure. So if we specify a -1 as an offset, -1 removes C and we go back to AB, right? So this would be the diagram that represents that, and what we end up with now are things back on the list that they came from. All right. So let's use the shift paths, and the idea here is that, again, we need to get our points back to be coordinated with the curve that they're located on. So the shift paths object is under tree shift paths up here at the top. We have a single offset, and remember, if we have A, B, -1 is going to go this direction and remove B. And that's exactly what we want. That's the default. So the tree branch is going to go into here. And now, instead of multiple branches, 18 branches with varying lengths of points stored on each path, we now have 4 paths, each with a list of points on it, right? And that's going to correspond really well with the original set of grafted curves. All right, so what I want to do here is I need to bring this set of grafted curves all the way over here. So my little tip for doing that is to grab a curve container. It's under params geometry curve. I'm going to connect the graft to the curve and bring it all the way over here. And I want to keep my file nice and tidy, so I'm also going to right-click and say turn the wire display to faint. All right, so and then I'll label these the grafted curves. All right, and these are our points per curve. All right. So if I were to go back to each curve, right, I need to move from points which are in X, Y, Z back to the curve parameter space. So I'm going to go to the curve analysis, curve CP, and what this will allow me to do is from the points go to the curve, and this gives me the T value. And with that T value, I can evaluate the curve for a lot of different properties. And I'm specifically interested in, we could do horizontal frame or evaluate curve. I'll use that one. So I'm going to evaluate each of these curves at the corresponding T values. Okay, now if I turn the previews off here, we can see what we get. This gives us the points in X, Y, Z space, which are the same as back here. But that's okay, because what we really want is the tangent vector. So I'm going to visualize this vector really quick. If we go to the vector tabs, vector subtab, vector display, and I anchor this set of points to these vectors, right, I can see that for each one of these, I now have a vector that is showing me along each curve, right? This one curve is drawn this direction, so these vectors are moving in this direction. And I also have the same ones for my other curve, right? And this is the kind of issue that I was mentioning before. By maintaining your data structure as you go with this curve intersect, it allows us to do this for both of the curves at every intersection point, which is a little bit of a kind of complex situation that you're dealing with. All right, so we have these different vectors that are corresponding to each curve, and the thing that's that we wanted to do is to draw a rectangle. So let's go ahead and draw a rectangle. If we gather the from the curve primitive rectangle object, this asks for a plane, an X size, and a Y size. So what I'm going to do is I'm going to create a plane from this object here, from the vector. If I go to vector, plane, I can compose a plane from X and Y axes. So here's my point, here's my X axis, and if I use that, I can draw a rectangle at every one of those intersections, right? Now I've just got to specify what I want to be the values for the width and height. So I'm going to just grab a regular slider for X. So this will grow its length, and maybe I'll make this go up to 12 based on the scale of my file. Right, so that's its length, and now I need to specify its width. So I'll copy and paste. So go into Y, something a little bit smaller. So the preview off here. So now I have rectangles going in the direction of the curve of each one of these intersections. And of course, this maintains despite the intersections, where they occur, etc. All right, and now you could continue to do something of interest with these rectangles or the directions, etc. But you've controlled very specifically what's happening at each location across the data structure. All right, so let's take a minute to review any questions you might have. Again, the things that we were doing with the data trees, we were querying certain conditions within the data tree by decomposing the path into its various index values and then testing them for equality. Retrieving only specific branches, shifting our tree back one level so that we can have all of our points organized per curve, and then go back to the curve to find some information that we can create some geometry with. So if you have any questions, go ahead and drop them into the questions panel, and we'll review them before we move on to the next exercise. And I'll go ahead and add the labels for this. This is curve CP. That was evaluate curve. This is plane. And here we have rectangle. All right, and I'll save this as our manipulating data trees working file. All right, save and close. Move that over. All right. So let's go ahead and talk about our next exercise.